All right, so in today's section 2.2, we're going to talk about what polynomial functions are and some of the main characteristics that they have. So we talk about end behavior and what that means, zeros and multiplicities and what that means, what is the intermediate value theorem, and I'm going to do a brief example, but I'm not going to go into great detail because you'll do this later on in calculus, and then we're going to talk about how we actually sketch these different polynomials. So when you start off with polynomials, and poly meaning multiple, it's a function such that it has the following form. All right, and I'm going to break this down. There's a lot of notation and a lot of things that we want to make sure we understand. So n is, so here we are, let n be, this is let n be an element of the integers of the positive integers. And so in math, mathematicians like to shorthand everything, and even I like to shorthand everything. It's a lot quicker to write this little piece than to write out what I just wrote out. So this little e here means element of, meaning that it belongs in a group or a set, usually when we talk about sets. And then this little double struck z here indicates the integers. And then this positive indicates integers greater than 0. So integers are whole numbers, but they can be both positive and negative. So technically this is a whole number, whole number. But I'm just using the positive integers as an example in this one. And then your a's are going to be the coefficients in your polynomial. So you just have to make sure that they're in the real numbers. So you can't have any imaginary numbers. That's basically what that's saying. And then this is the general form of polynomial. So you have f of x equals a sub n, so whichever coefficient, they're just a placeholder, x to the nth power. N is going to be the highest power degree. And then it descends all the way down to just even adding a constant down here. Now that's the way the book likes to write it, is in descending order. Typically when I like to write polynomials, I will start off with the smallest value and go in ascending order all the way up to the highest value. So I kind of just swap it around, which doesn't really make a difference. It really doesn't. It really doesn't make a difference as long as you know what the highest degree is. So this form is what you'll mostly see it in, but when you like cook up polynomials and stuff, this is usually the form that you'll see it in, this one here. Usually in like coding and stuff and other kinds of like theorems and applications in like applied math is usually used that way. Okay, so these are polynomial functions of degree n. So usually when you have some type of function, polynomial, you always refer to it as a degree whatever polynomial, and that degree whatever that you state is the highest degree in your polynomial. The exponents and the coefficients must be real. Exponents have to be positive. Coefficients must just be real. So here's some examples of polynomials. We have g of x is 3x to the 5th plus 2x squared plus 1. It's just a standard x to the 5th equation. We've got h of x is equaling negative 2x to the 2nd power plus 3x to the 6th plus 52x. That's another example of polynomial. You can have negative coefficients, totally fine. What you cannot have in polynomials, so these are examples of not polynomials, are fraction exponents, which also correspond to radicals. We can't have that. In t of x here, we have x to the negative 1 power. You're not allowed to have any negative exponents, just not allowed. And you're not allowed to have imaginary numbers either. So there we have I, we have the negative exponent, we have a radical over here. So just generally, you can't have those polynomials. All the coefficients must be real numbers. So they can be square roots, but they just can't be imaginary. And all of the x have to have a positive number. That is a whole number. no fractions, no decimals, no negatives. That is the main kind of conditions for polynomials. So we've studied so far the constant function, which is technically x to the 0 power, because x to the 0 is always 1. Anything to the 0 power is always 1. And for example, if we have f of x equaling 2, right, that might be some type of a constant line, right? So that's an example. We call it degree 0. It does not have any x's in it. The domain is all real numbers. You can plug in any value for x, and you're always going to get out 2. 2 is going to be the range, because it's just that singular y value. So that's going to be our constant function. Notice it does have that domain of negative infinity to positive infinity. Then we studied linear functions, which were x to the first power, so degree 1. And so say we have 3x plus 1, right? We'll have some type of a line that looks maybe something like that. And our domain for linear equations was all real numbers, so negative infinity, positive infinity. The range was also negative infinity to positive infinity. So keep that in mind as well. The next function that we studied was a quadratic function, so an x squared. So say we had f of x equaling 2x squared minus 1. Domain, again, all real numbers, so negative infinity to positive infinity. And then the range is going to be that negative 1 to infinity. We call this a degree 2 function, degree 2. Then we studied a cubic function, right? We have f of x equaling x to the third plus 2. That was a parent function in our set that we had of all those different parent functions. The domain is negative infinity to positive infinity. And our range is also negative infinity to positive infinity. All right. So those are just some of the functions we've studied so far. And if you notice, every single one of these functions has domains that are all real numbers. And so the domains of polynomials are always all real numbers. Remember, the only two conditions that make functions not have a continuous domain or have some type of break or an entire segment missing are radicals and fractions. And if we eliminate those, it should make sense that our domain is going to be all real numbers always. Now, graphs of polynomial functions are always continuous and smooth. Sharp points, like absolute value, cause non-smoothness. Smoothness means that you can go continuously and you're never having some type of sharp cusp. So sometimes there's functions that do exist that could possibly be something like this. Something like where it has some type of sharp cusp like that. They usually have a name of elliptic curves, and they usually happen when x and y have higher powers. So it's a non-explicit type of formula that you would get for some type of a function. And so we don't really study that in this course, and you really don't study it too much in undergraduate level mathematics. So you won't really have to worry about non-smoothness in functions. The only thing is absolute value at that initial point and certain piecewise functions depending on how they're joined together. Sometimes they're also sharp and don't have that smoothness, so they have cusps sometimes. Okay, so functions like 1 over x and piecewise functions, though, are not always continuous. And by continuous, I mean at any point of your function, you can always travel along the curve with your finger, and you never have to lift up and move to something else. So, for example, for a continuous curve, right, if I were to draw, say, x squared, right, I go down, let's start over here, I go down, and I go back up. Right, so I don't really have to worry about that. Now, if I were to draw 1 over x, though, so if I were to draw 1 over x, right, I know that that looks like this, right? So it goes down over here. But I have to pick up my pencil and to draw that the rest of the graph, right? I have to pick up my pencil. And so that's kind of the continuous aspect, is can you draw it without lifting up your pencil? That's kind of the idea behind continuity and continuous functions. Now, continuous has some very interesting properties, and so you'll learn that later on in what it means. So continuous. Keep that in mind of what continuous actually means. Now, we're going to do a lot of analysis of polynomials, and we're going to understand a lot of different things, and I'm going to introduce this new notation to you and what we call end behavior. And so just keep in mind that whenever you're approaching values, right, sometimes you cannot plug in a huge function, a huge value into a function and graph it. You just simply don't have the space. So you kind of have to analyze like where the x values are going to go or the y values as you plug in those giant x values. All right, so to start our analysis of these polynomials, we have this function here, f of x equals ax to the n, right? A is a real number, n is some positive integer. So let's graph a few of these functions that we will have, right? And so let's start off with x squared. And so if I draw x squared, personally, I know x squared is a line that goes through the origin. So I'm just going to draw that line. Okay, let's draw x squared. Okay, I'll just draw my x squared here, and I want to make this side a little bit smoother. Okay, so there's my x squared function. Let's draw my x to the third. We know that it's gonna go like this, and it's gonna go like that. Okay, I'm gonna draw this piece a little bit more like that. Okay, let's draw x to the fourth. This guy is going, so x to the fourth is also going to look like a U shape. Okay. And then let's draw x to the fifth. And if you were to plug this in, it's also going to look quite like this. Okay, so there's all those functions. And if I were to graph x to the sixth power, you would imagine that I would have something kind of like this. X to the 6 is going to kind of plateau and then shoot up. So what's going on is every time you increase the degree, depending on if that degree is even or odd, it's going to look like either a parabola or a cubic function, right? So it's either going to be a U or this. That's the only two kinds of ways that the polynomials will look like with their end behavior, with the way that the ends of the graphs are going to look. Now, of course, we do have to keep in consideration, right, reflections. So if it's negative, and then if it's negative there, right, it'll reflect down. So we do have to keep that in mind. But overall, it's either going to look like a parabola or a cubic function. So that's really all we have. Those are the two that we have to worry about. Is it even or is it odd? So here's some notation, what we call infinite behavior. And so as x approaches the positive infinity, right, that's going to be as your x values in your curve or in your graph approach this way. So here's the positive infinity of your x. So as your graph approaches this, so as you plug in those x values here, all of these x values, what is the y values going? Are they going up or are they going down? It's essentially what you're worried about. And so we have that same idea for the negative infinity. As x approaches negative infinity, you're approaching it from the origin. So you're always starting from the center. Okay. And then as f of x approaches infinity, remember that's just as y approaches infinity, it goes up. And as f of x approaches negative infinity, right, that's this direction. So that's the notation that we're going to use for infinite behavior. It's going to be x, a little arrow, and then the infinity symbol that is appropriate. All right, so when you have a polynomial, the leading term will dictate the overall behavior. So whatever the highest power is, right, which is our leading term, that dictates the overall behavior of the entire polynomial. So here's from the textbook, a nice little graph here that gives you all the conditions. And so they use their fancy notation. But what we want to just know is the end behavior. Is it going to look like a quadratic or a parabola, or is it going to look like our cubic function? And so you can see here, if n is even, that means if the power of your polynomial is even. So if it's to the second, to the fourth, to sixth, etc., etc. It's going to have this end behavior if the top coefficient or the first coefficient is positive. So example, if you have 3x to the 6th power, 2x to the 4th, 3x squared. These are all examples of what would follow in this. This one would be maybe negative 3x to the 8th, maybe negative 5x squared, maybe negative 1/2 x to the 4th, and etc. This one is going to be maybe 3x to the 5th, let's say 9x to the 3rd, and this one's going to be maybe like negative 4x to the 7th, and then, I don't know, maybe negative 1/9 x to the 5th. So those are examples of what exactly the end behavior is going to look like. So that's important for us because in order to graph polynomials, you have to do it in steps. So you're going to have to find the end behavior, you're going to have to find the roots, you're going to have to find this, and then you can graph it. So it's a lot more work. So let's determine the end behavior of this function. So the first thing we look at, what is our leading term? So we have this term here, that's not our leading term. We have this term here, not our leading term because the power is too small. This term here is our leading term because it has the highest power to the 7th. So we have negative 2x to the 7th. First, we look at the exponent. Exponent, odd. Then we look at coefficient. So the a sub n value is negative. So now we look back at our chart, right? We look to see, okay, odd, n is odd, and a sub n is negative. So we have this case. So our end behavior is up, left, down, right. Or as x approaches infinity, comma, f of x approaches negative infinity. That's what this is saying. And then as x approaches negative infinity, comma, f of x approaches infinity. So they're always opposite to each other. So that's how you would write mathematically, and this is common, like just everyday language we would use. Okay, let's do this next one. B. H of x equals 1/2 x times x plus 3 to the 4th times 2x plus 1 to the 3rd. So first thing we look is we look for our leading term, and we notice that we don't have a leading term. So what we have to do is we need to count up these exponents that we have. And then don't forget this one out here. So I have 3, 4, and 1. If I were to multiply all of those powers together, right, if I were to FOIL this out, I'd get x to the 4th plus other things that I don't care about. If I were to FOIL this out, I would get my highest power to be 2 times 8x to the 3rd times blah, 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 right? And then I'd have this x to the 1st. So essentially what I'm doing is just shorthand multiplying all these together because I don't care about all those other terms. I just care about the first leading term. So the highest power for me is going to be 8x to the 8th. We just add up all those exponents. So it's x to the 8th, and we look to see, is it negative? No, and none of the other ones had negatives. So exponent, even, a sub n, positive. So we look back at our chart, and we have up, left, up, right. Or as x approaches infinity, comma, f of x approaches infinity, and as x approaches negative infinity, comma, f of x approaches infinity. So they're both going to be infinity values. That's just kind of how it is. All right, so that's going to be how we're classifying end behavior. Okay, so now we have zeros and multiplicities. So with any polynomial, there is a theorem that talks about x-intercepts. And so if you remember from algebra courses, if you have an equation that has a singular x in it, you're expected one solution. If you have an x to the second power, you're expecting at least, or I should say at most, 2 solutions. Now, of course, we have to take into account no solutions, repeated solutions, and then 2 distinct solutions. If we have x to the third, we're expecting at most 3 solutions. And the list goes on. As you get bigger, so if you have x to the n, expect at most n solutions. Now again, this is what you're expecting at most. So this is not guaranteed that you get a 1 solution, 2 solutions, 3 solutions, n solutions. This is just saying that you can have that many solutions. You could, hypothetically. But it's not going to happen every time. So when you're given any polynomial, we classify the x-intercepts every time it hits the x-axis, or those solutions to the equation, as roots. We call them roots. There are fields dedicated to finding polynomial roots. We call it root finding. There's many, many theorems using that intermediate value theorem. There's Euler's and Newton's method. And that's probably one of the most famous methods of finding roots. Like there's whole semesters in graduate school dedicated to root finding, and there's degrees dedicated to root finding. It's a huge topic in engineering because these roots actually supply stability for certain kinds of equations, and there's lots of other applications. But for the context of what we need is to have a great foundation for any type of successful career in the STEM field. We need to just understand what a root is, so that when this comes up in later on in life, you understand at the deeper level and at the base level what a root is. And so, again, roots are just x-intercepts. That's all it is. We just call them roots instead of x-intercepts because it kind of sounds cooler. So let's determine the roots of this function. So we're given this function, so we need to determine the roots. First thing I'm going to do is look at my function, and it's already pretty much factored, but the one thing I'm going to do is take this and notice it's a difference of squares and factor it down one more time. Now what I'm going to do is I'm going to set each one of those equal to 0 and solve. So x minus 3 equals 0. X plus 3 equals 0, x plus 5 equals 0, and x minus 1 equals 0. I set all those equal to 0, solve, so I've got x equals 3, negative 5, and 1. That is all of my roots. And so if you notice, this is an x to the 4th polynomial, so this is a 4th degree polynomial. And I got 4 solutions. So keep that in mind. All right, determine the roots of this function here. Okay, well, I don't have this factored. I can't just peel it off and set it equal to 0, right? Because I'm setting the whole thing equal to 0. So I need to figure out what to do with this. Now, luckily for me, I remember that when I have 4 terms that look like that, I can factor by grouping. So let's factor by grouping. So I'm going to factor out an x squared. So I get x plus 1, minus, I'm going to factor out a minus 9, so I get x plus 1. Oh, this is perfect. It factors great. So I get x squared minus 9, x plus 1. Perfect. Set that equal to 0. Solve each factor. I'm going to get this factored even more. X minus 3, x plus 3, and x plus 1 equals 0. So I get x equals negative 3, and negative 1. So I have 3 roots. Those are my roots. And notice that I have a degree 3 polynomial, and I got 3 roots. Okay, let's determine the roots from this polynomial. So we have x times all of this. It's all prefactored, so let's set it equal to 0. So we got x times 5x plus 1 squared, x plus 3 to the 6th equals 0. I got x equals 0. 5x plus 1 to the 2nd power equals 0. And I got x plus 3 to the 6 equals 0. These exponents don't make a difference, so I'm going to have 5x plus 1 equals 0. And I got 5x equals negative 1, x equals negative 1/5. Same thing with this one. I'm just going to get x equals negative 3. So my roots are x equaling 0, comma, negative 1/5, and negative 3. Now notice, though, that I have a degree 6, 7, 8, 9, degree 9, but I did not have 9 solutions. Well, that's because some of those roots were repeated, right? Technically speaking, I have a couple of them that were repeated. So if I were to take this x plus 3, right? This is x plus 3 times x plus 3 times x plus 3, right? 6 times, that's 6 roots that I have there technically. So when we have repeated roots, we classify them as the following. If the 0 or the root of it is odd, it has an odd number multiplicity, so we call the amount of times it repeats a multiplicity. So if we look back at our problem here, this negative 1/5 has a multiplicity of 2 because that's the power on it. We have this x equaling negative 3 that has a multiplicity of 6. And this x equaling 0 has a multiplicity of 1. That's what that means. If the root is an odd multiplicity, so we only had technically, I think, one, the x equaling 0 would be an odd multiplicity. That would mean that the graph crosses there. Now think about it. If you think about x to the third, this crosses the x-axis. It's an odd power. Now, if you have a 0 that is an even multiplicity, think x squared. X squared at its root doesn't touch it. It doesn't cross it. It simply touches that origin. And so that's how I like to remember mine whenever I have to classify multiplicities. So if it's an even multiplicity, it's going to just simply touch and turn back around. It does not cross. So it'll have like a little cup type thing there. Okay, so let's find the zeros and classify them and talk about what that means for us. So this has a coefficient. We don't care about this. It makes no difference. So we set this x minus 4 equal to 0. So I get x equals 4 call it, or we can say m equals, actually we'll call it multiplicity, equals 2. That's the power. Okay, we have this 2x plus 3. That gives me x equals negative 3 over 2. Multiplicity of 5. So we have a multiplicity of 2, and we have a multiplicity of 5. Okay, right? And we get that from 2x plus 3 equals 0. And that gives me 2x equals negative 3. X equals negative 3 over 2. Okay. All right, now we need to classify. Does it touch or is it cross? So we look at our graph here, or our little chart. If it's a multiplicity even, 2 is even, this is going to touch. If it's a multiplicity odd, it's going to cross. Okay. All right, so that is how we determine the zeros and classify them as such. Okay, that's all we have to do. All right, now again, not all polynomials are given to us in factored form, so we are going to do like some other methods for root finding, which can be quite annoying and tedious, but sometimes when you don't have a factored polynomial, you have to do some other methods. So we'll learn that, I think, in section like 2.4 and 2.5. Okay, so let's talk about the intermediate value theorem. So the intermediate value theorem is has a couple different conditions. So first of all, it must be a polynomial. Usually speaking, it must be a polynomial. And you must be looking between some type of an interval on your graph of your polynomial. So here I have this kind of curvy function, and it's going from A to B, and A and B are my interval. So A to B is my interval here, right? This is my distance. And so essentially what the intermediate value theorem says is that if you have an interval, A to B, right, so some values, if you evaluate your endpoint, so this is my function f of x, call this f of x. If you evaluate f of a over here, so f of a is down here, and you evaluate f of b, and you realize that f of a is having a different sign, so in this case f of a is going to be negative, and f of b is positive. If they have different signs, then the function has at least 1, 0 on that interval. Now, this has to make sense because think about it. If the function value is changing from a negative to a positive, it has to cross the x-axis somewhere, right? Your function can't just skip and go back up. That's the definition of a polynomial, right? It's continuous everywhere, so you can't have any breaks. And so that's kind of why you can use this theorem, because it's a polynomial. You're given it's continuous and it doesn't have any non-smooth parts to it. So if the sign of your y's are different from each other, then you are allowed, you have a root. You will find some type of root. And so this is actually one of the main ideas for root finding, is that if you can code this up very easily. If you give your code, so I've done it many times in Python, if you just run a function that evaluates a specific interval and tests if A is less than 0, if B is less than 0, if the signs are different, right? There's ways to write that. And then you can say, okay, well then there's a 0, but you can't necessarily immediately find the 0. You start splitting those intervals in half, right, depending on where it is, and you kind of like get the 0 into such a small interval that it could, what we say is it converges. And so that's the idea behind using this intermediate value theorem into practical applications. So here's the general, this is the actual theorem for the intermediate value theorem. And so that's just the formal definition. Okay, so let's actually use this in a question. So on this interval, for f of x equaling negative 2x squared plus 1, is there a 0? Can we find a 0? Now, again, we're not going to find the 0. We could totally, but we don't want to. We just are asked, is there a 0? We need to answer with a yes or no. And if there's a no, we need to show why. If there's a yes, we need to show why. In math, you cannot just say yes or no. You need to explain your answer. We like to be as thorough as possible. Okay, so let's evaluate f of 0. It's a first step. Evaluate the first value. So f of 0 is going to be negative 2. Change back to red. Negative 2 times 0 squared plus 1. I get 1. All right, let's do f of 3. I get negative 2 times 3 squared plus 1. That gives me negative 2 times 9 plus 1, negative 18 plus 1, which gives me negative 17. Does one of them have a different sign than the other? Yes, f of 0 is positive, and f of 3 is negative. So yes, there is a root. Now, of course, we don't know what the root is. We could set it equal to 0 and solve. We could, if we really wanted to. But we don't want to. We don't want to solve that. All right, now let's talk about putting all this information together in Sketch. So there's this little tidbit of information about turning points. You can kind of ignore that. I mean, it's a good thing to understand and know, but turning points are just how many times does the function change direction, meaning like is it increasing, decreasing, increasing, decreasing, kind of stuff like that. So, all right, so here's the general formula / methods outline of how to graph a polynomial. So first, use the leading term to dictate what's the end behavior. Is it going to look like a u? Is it going to look like an upside down u? Is it going to look like our x to the third, or is it going to look like the reflected x to the third? That's the first thing you determine. Determine the y-intercept. Evaluate f of 0. Plug in 0 to your function and figure out what that is. Determine the zeros. So factor if you're able to, right? Factor the function if you can. Plot the x and y intercepts. Now, when you plot the x and y intercepts, determine if they have even or odd multiplicities and if they are crossing or touching. You can test for symmetry if you want to. That's great. And then the more plots that you point, the greater level of accuracy. But we're sketching in this class, so you don't really need to plot too many points. So let's graph this function from start to finish. First thing, let's find our end behavior. Okay, so negative, so a sub n, negative. Okay, now we need to determine n value. So x to the n is equal to, what's the nth power? What's the power? Leading term. So I have a 2, I have a 1, this is technically 1, and this is technically 1. So 2, 3, 4, this is 4. So n equals 4. So our leading term, so our highest power is 4, which is even. So since it's negative and it's even, it's going to look like this. Okay, so right, down, left, down. Okay, that's what we have. Okay, so let's kind of draw out our graph, I guess we could. Let's wait a sec. Okay, let's find our zeros too. Let's find zeros. Okay. So let's set the whole thing equals 0. Now this negative 1 over 10 does not matter. Does not matter for that. We don't care about that. So we just need to set this equal. So we have x equals 1. X equals 1. This is a multiplicity of 1. X equaling negative 2, comma, multiplicity of 1. And we have x equals 4, multiplicity of 2. All right, so that's what we have for our zeros, right? Setting each one of those factors equal to 0. Let's find our y-intercept. So f of 0. So we get negative 1/10 times 0 minus 1 times 0 plus 2 times 0 minus 4 squared. So I get negative 1/10 times negative 1 times 2 times negative 4 squared. So we get 1/10 times 2 times, what is this, 16? 16. So this cancels, so I'm left with 16 over 5, which is going to be approximately 3 point something. All right, so 1/5, 3.2, roughly-ish. So a little bit bigger than 3. Okay, so that's our, so it's 3.2, so that's what we're going to get. Okay, so let's actually start graphing this now. So draw out our graph, and let's draw. Okay, so at 0 we have for our y value 3.2, so we'll just graph that up here. We'll say this is 3.2. We have x equaling 1, so here's 1. We have x equals negative 2. And we have x equaling 4. So we'll say 4 is over here. Okay, we have a touch point. So remember, if it's multiplicity of 1, cross, cross. If it's multiplicity of, or odd, if it's even, we have a touch. So it's going to touch at x equaling 4. So I'm going to write this little cup here. That's usually what we'll do. And since this is the last point, I know that my end behavior is going to look like that there. So now I need to go, and I know that my end behavior, right, is left down, right down. So they're both coming down. So that means that this is going to go to here. So that's what my end behavior is going to look like. Now at x equaling negative 2, it's going to be a cross. Okay, so it's going to cross there. So it's going to go up here. So it's going to touch at that x-intercept. It's going to go back down. It's going to cross here, and it's going to connect there. So that's what I'm expecting to get for graphing this kind of function. Now, again, this is a rough sketch, so it's not perfect, but it's good enough to kind of visualize exactly what's going on. All right, so that's how we would want to graph a polynomial.